Energy is the ability to do work. If you can apply a force on something in the same direction that you displace it, or at least a parallel direction that you displace it, then you have energy. And that's what energy is. It's just the ability to do work. Energy is a scalar, work is a scalar, energy is a scalar, so that's really nice because then we never have to break it up into its x and y components and all that stuff. Another thing you probably know about energy because you've covered it in Science 10 and other science classes is that energy is always conserved. So the total energy after the process is the same as before a process, right? So energy is always conserved. It's just converted from one type of energy to a different type of energy. But there's no such thing as creating or destroying energy. We can't do that. We can just convert it from different forms. So all forms can either be classified as kinetic energy or potential. Kinetic's pretty easy. Kinetic energy is just the energy of motion. Is something moving? Okay, it has kinetic energy, and that's that. So that's equal to 1/2 mv squared. I know you guys have seen that one before, and it's pretty self-explanatory. So EK, I put the little K there so we know that it's kinetic, and that's measured in joules. M is, of course, the mass of the thing that's moving, and V is its velocity that it's moving with. So we've all seen that one before. Let's move on. We have potential energy, and this can come in many different forms. In Physics 20, we're going to focus on 2 specific types of potential energy, okay? And so, of course, this is just, there's stored energy due to position. So the one that you know about most is gravitational potential energy, and that's when if something's held above the Earth, then it has energy because gravity has the potential to do work on that, right? So if it has the ability to do work when released from a height, then it has gravitational potential energy. So, right, if I set a pencil on my desk, sure, it could still fall onto the floor if it falls off the desk, but at this point, we would not say it has gravitational potential energy because it's resting on the desk, and that is the nearest kind of ground as far as it goes. And then all of a sudden, if I hold it over the desk, though, then of course it has potential energy to fall down to the ground. Okay, and so of course sometimes it's above the Earth or above a certain point on the Earth, right? We choose whatever is the closest ground to the thing that we're holding up. Okay, so of course it's the product of weight of the object and the height above the reference level. Okay, so again, the reference level can be arbitrarily chosen. It's not really arbitrary though, because again, if I hold a pencil above my desk, right above my desk, it's likely it's going to fall down to my desk, and there's not going to be some crazy wind gusting in through my classroom that's going to make the pencil fall over the desk, right? But if I hold it above the floor, then of course my reference level for what it's falling to is the floor and not my desk. Okay? So keep that in mind. So as long as the reference level you're choosing remains constant throughout the entire analysis of its motion, then you're great. Then you're fine, right? But I think we know that. We know that from Science 10. We did go over it then. So yes, potential energy is weight times the height. What was weight again? That's mass times gravitational acceleration times height. So therefore, look at that, mgh. Makes a lot of sense. So of course, I put a little p down there so we know we're talking about potential energy. But in this case, we're going to talk specifically about gravitational potential energy. M is, of course, mass. G is 9.81. And H is, of course, height. The path, by the way, to the height is not important. We just want the most direct height downwards because that's how it's going to fall. But if I lift something up, not directly upwards, but kind of waving it around a little bit, that doesn't matter. I just know that when it falls, it's going to fall directly down. Okay, so I only need that height from the most direct path to the ground. Okay? And then finally, elastic potential energy is the other kind of potential energy that we're going to go over in Physics 20. What is this? So when you compress or stretch spring, guess what? It wants to go back to what we call its equilibrium. So if I compress a string and then put an object there and then I let the spring go, of course the object is going to move. So when I compress the spring, it has stored potential energy. And then it can move something else. It can cause something else to move. So therefore, that is stored potential energy when a spring is stretched or compressed. Okay, so of course it can do work on an object when it's released. So this could be a spring, this could be like an elastic band. That has stored potential energy. You stretch an elastic band and then you let it go and you hit your friend with it. It did work, right? So that is elastic potential energy. So how do we calculate that? So here I'm using the subscript S for springs, okay? Just a note, your data sheet says P. So it actually has two EPs on there. Remember, they're not the same thing. I can't just make one equal to the other because spring potential energy is different than gravitational potential energy. Okay, so just a little note there. Okay, so that's equal to 1/2 kx squared. You're going, okay, what the heck are all those? Because this is the first time I've seen this formula. So ES, again, is elastic potential energy, still in joules because all energy and work is measured in joules. K is a spring constant, so that's going to be different for every spring, every elastic that you work with, right? So that depends on the spring or it depends on the elastic, right? How well can you compress it or stretch it? Some springs are really easy to compress and stretch. Some springs are really, really difficult to compress and stretch, okay? So the spring constant is going to be different for every spring. And then X is how much you displace the spring. Okay, so that's displacement of the spring. Okay, so if the spring is normally like 10 centimeters long and you compress it so it's 5 centimeters long, then your displacement was 5 centimeters, right? If your spring's normally 10 centimeters long, you stretch it so it's now 14 centimeters long, then your displacement is 4 centimeters, okay? So that's what displacement means. So let's do an example. I don't want to just do an example where we plug numbers into formulas because honestly, these formulas are pretty straightforward and two of them you've actually worked with a lot, right? Gravitational potential and kinetic energy. So I'm not going to do any questions with this right now. Don't worry, we will more in further lessons. But at this point, I just want you to kind of make sure you know about these equations and when they would be used in certain situations. Okay? But here's a proportionality example because I think proportionality always helps. So a spring in a trampoline has the ability to store 1.52 joules of energy. Good to know. So that's how much energy it has, or how much potential energy it has. If the spring is replaced and the new spring constant is half the value while the displacement is tripled, determine the potential energy the new spring has the ability to store. Okay? So I want to know how is energy proportional to that spring displacement and its spring constant and its displacement. So I know spring energy is equal to 1/2 kx squared. Okay, so if I want to know proportionality, I ignore everything else except for what I'm looking at the proportionality with. Okay, so the 1/2 is not changing and it has nothing to do with the proportionality, so I'm going to completely ignore it. So I know spring potential energy is directly proportional to K, but I also care about X because I know spring constant is half, displacement is tripled. So I actually want to know what if I do both of that. So I need kind of, instead of two different statements, I know that spring potential energy is proportional to K, but it's also proportional to X squared, and those are multiplied usually. Okay, so if I want to know my new spring potential, I need to half the spring constant and triple the displacement that it can be displaced. Okay, so what does that mean? K is going to be half as much. The spring constant was x, so that's going to be tripled, but since x is usually squared, I have to square it. Okay, so my new spring potential will be how many times as much as my old one, and that's what this is going to get. So 1/2 times 3 squared, well, 3 squared is 9, and then times 1/2 is 4.5. So what does that mean? It means the new potential energy in the spring is 4 times as much as the old one. And that's all I need to know. So I go 4.5, and the old one could store 1.52 joules. I don't know why this is moving around so much today. 1.52 joules. There we go. And what we get is 6.84 joules. So this spring can store a bunch more energy, which is nice. So really, it doesn't matter if the spring constant goes down. If you can displace it more, that's huge, right? So this trampoline could get pretty crazy if you can displace it 3 times as much. Yikes. All right, and there we go. So that is how you deal with proportionality examples. So please don't forget about proportionality. It's going to keep showing up. It's going to keep rearing its ugly head over and over and over. Okay? But that's also, remember, K, spring constant, and X is the displacement of the spring. Okay? And that's it for energy types. Just a note, there are other types of potential energy. Okay? It's just the only ones we're going over in Physics 20 are gravitational potential and spring potential. Okay? So, just so you know, more than just those for potential energy.